go ahead and get started here. So this one we're going to talk about Gibbs free energy. And this is a very, very useful concept when we're talking about thermodynamics. So this is just kind of a review from what we talked about at the end yesterday. So universe is basically system and surroundings. Remember, system is whatever we define the system to be. So it doesn't matter what it is. If your system is a cup sitting on my desk, surroundings is everything else in the universe besides that cup. Okay. If you total up the delta S of the universe, it equals the delta S of the system plus the delta S of the surroundings. And for spontaneous processes, delta S of the universe is always greater than 0. All right? So, and I'm not sure if you were all here when I talked about this, but it's kind of a depressing thought a little bit that no matter what you do, you are increasing the delta S of the universe. Or at the very least, you are keeping the delta S of the universe the same. All right? So you clean your room, you have increased the entropy of the entire universe by doing so. All right? So we should just stop cleaning our rooms, is what I'm saying. It's the most responsible thing to do, really. So just looking at, and you don't have to remember all of this. This is just some derivation stuff. But the delta S of the surroundings is the opposite of the heat of the system divided by T. And again, we really haven't talked about that equation because I don't think you're going to need to use it. But I'm just showing you how they get Gibbs free energy here. At constant pressure, Q is equal to delta H. I don't know if you remember that from our first thermochem unit. But the heat is equal to the delta H when we're at constant pressure, which is most of the time in this class. And so then you can change that because you've got delta S of the surroundings up here, so you can, basically plug this in. Well, I mean, essentially, this plugs into here, and then you can plug that into here, and you get negative delta H of the system over T. And then rearrange that a little bit to get rid of the fraction, and you end up with this equation right here. Negative T times the delta S of the universe is equal to delta H of the system minus T times the delta S of the system. Okay? Now, remember what I just said. The delta S of the universe is always, for spontaneous process, it's always what? Greater than 0, right? So this number is going to be greater than 0. Okay? So then you can actually use this T times delta S of the universe, and we can call that Gibbs free energy. Okay? And that tells us something really useful about the spontaneity of a reaction, whether it's going to be spontaneous or not. So ultimately, if your delta G is let's get this mixed up. If your delta G is positive, then that means it's not a spontaneous process. If your delta G is negative, then it is spontaneous. Okay? Oh, I guess it's right there. So when the delta S of the universe is positive, delta G is negative. So that means when delta G is negative, a process is spontaneous. Okay? So the sign of delta G is a really important thing. The size of delta G can tell you something as well. It can tell you how spontaneous it is. In other words, kind of how readily something will react without outside intervention. Some reactions are a lot more spontaneous than others. So if delta G is negative, then the forward reaction is spontaneous. If delta G is 0, system is at equilibrium. And if delta G is positive, the reaction is spontaneous in the reverse direction. Okay? So it's always spontaneous in one direction or another. Just depends on when we're talking about an equilibrium reaction, your delta G will basically tell you which direction it is spontaneous in. Okay? And they always, the analogy here is kind of like a ball rolling down a hill. Okay? You can start the ball on the hill on the left here, right? and the ball is going to roll down towards the middle until it gets to equilibrium, right? Or you can start the ball on this side, and it's going to roll down the hill till it gets to equilibrium. It doesn't really matter which side you start the ball on. It's going to end up in the same place ultimately. Okay? So by that analogy, the reaction, I don't know if you can see this very well or not, but the reaction here is the Haber process, which is nitrogen plus hydrogen makes ammonia. You could start with N2 and H2, right? Put those two together, and they are going to eventually react spontaneously to reach equilibrium if you're going in this direction. Or you could start with just NH3, and that's going to react spontaneously to reach equilibrium from this direction. Okay. So that's kind of the idea. So delta G basically tells you 1 is the system at equilibrium, because if delta G is 0, the system is at equilibrium. But it will also tell you which direction is the reaction spontaneous in. Okay, so this is very much related to equilibrium.
The bus for the student council trip to be outside the cafeteria momentarily.
Okay, so standard free energy change, guess what? You can do the same thing with delta G as you could do with delta H and with delta S, or I guess just with S. You can use delta G of formation, standard free energies of formation, to solve for delta G of a reaction. Okay? So if you know the delta G is a formation, you can take the products minus the reactants, and then that will give you the delta G for the overall equation. And based on the sign of that delta G, that will tell you whether it's spontaneous or not spontaneous. At temperatures other than 25 degrees Celsius. At temperatures other than 25. That doesn't make any sense. Oh, yeah, it does. Okay, I'm sorry. We're going to assume that our delta H and our delta S our delta H and our delta S don't change all that much with temperature, which is kind of not a perfect assumption, but we're essentially going to make that assumption. Am I already done with what I need to talk about?
Dancers should meet in a small gym now. Swapper dancers should meet in a small gym now.
I was angry a little bit. No, I guess I'm not done yet. There's kind of a little overlap between...
Whoever called about swapper dancers, please call the main office.
What? Sorry. I think something weird is happening. Because she just called about the Swafford dancers, and then she said, whoever called about the Swafford dancers, please call the main office. Or was it a Ooh, someone...
Swapper dancers do not go to the small gym. Just hold on, we'll find another place.
Okay. Sorry. All right. Anyway, sorry. That was kind of funny. So the question here is, looking at this equation, how does delta G change with temperature? And it kind of depends on what's going on with the delta H and what's going on with the delta S. Okay. Okay. Yeah. So I think we're on the right track here. It threw me because they started talking about temperature, and that's kind of what the next section is about. But so this problem here says calculate the standard free energy change for the formation of NO from N2 and O2, and they give you the delta H and the delta S for the reaction. Okay. So basically all you have to do, and this equation is on your equation sheet, you'll just want to use this equation right here, delta G equals delta H minus T delta S, and use that to figure out, the answer to this question. Okay, so delta G equals delta H. You got a couple choices here, all right? This is where you have to be really careful. Kilojoules is the unit for delta H. The typical unit for entropy is in joules, not kilojoules. So you have to be really careful when you're solving these problems. You've got to convert one or the other. I like, well, yeah, I think I like not having to use small decimals. So I don't know why. I just prefer bigger numbers rather than small decimals. It doesn't matter which way you go with this. You can change this into kilojoules if you want to, the joules, or you can change the kilojoules to joules. So I'm going to change this to 180,700 joules. That's the delta H in joules instead of in kilojoules. You know what? Sorry, changed my mind. I apologize. The reason I changed my mind is because delta G is usually reported in kilojoules, so we won't have to worry about doing conversion at the end if I keep them both in kilojoules. So that's probably the best procedure here. So 180.7 kilojoules minus T times delta S. The T needs to be in Kelvin temperature. Okay, so you got to watch your units on that as well because this is in joules per Kelvin for the entropy. So 298 K is our temperature here, times our delta S, which is 0.0247 joules per K. All right, so I just converted that, kilojoules per K. I just converted that into kilojoules. Kelvin's going to cancel out, so that leaves us with kilojoules for both, so we can subtract those two from one another. And then when you do that, then you're going to get a number. And I don't feel like calculating it right now, so I'm going to erase this work, and I'm just going to show you the work that they have on here. So they basically did the same thing. They just showed the extra step where they took 1 kilojoule divided by 1,000 joules, and they converted that into kilojoules. So you end up with the 180.7 minus 7.4, and that's going to be 173.3. Now notice they're paying attention to their sig figs there, right? You had 3 sig figs in both of these numbers. Well, are they paying attention to their sig figs? Is it exactly 7.4? 98 times 4.7 divided by 1,000. No, it's not. Why did they do that? Because technically, just from those, you got 3 sig figs in both of those numbers, so I would round that to 7.36, then subtract. So I guess they're not being careful with their sig figs there. But you're going to end up with 173.3 or something in the ballpark on that, okay? So the question is not, what's the value of delta G? The question is this reaction spontaneous under these circumstances? And the answer would be, no, okay? Because this is a positive number, right? If delta G is positive, it's not spontaneous. Now, it's not spontaneous in this direction, but what about in the other direction? It would be spontaneous in the other direction, okay? Okay, so their comment is what I was basically saying. And that's just another practice exercise, but it's basically the same thing. Okay, so then here's a practice where you're calculating, using the free energies of formation, you're calculating the standard free energy change. So they want to know what's the delta G for the reverse of the above reaction, and they're wanting you to look these up in Appendix C. But I'm just going to show you kind of the solution here. So the delta G of the PCl3, the delta G of formation for that one is negative 269.6. Which one did I say that was for? The PCl3. Negative 269.6. And again, notice the units here. These are kilojoules per mole. Okay, the P4 is Yes, 24.4 kilojoules per mole. And the Cl2 is 0. Interesting. Why is that 0? Any ideas? Okay, that's the elemental state for chlorine, right? That's the most common state that it has. So just like with the delta H of formations, when we have a delta G of formation, we kind of define certain elements. If they're in their natural state, we'll give those a value for delta G of formation of 0. Okay, so the same, you had to remember this for delta H of formation as well. You got to remember it for the delta G of formation, that anytime you have something in its elemental state, that's going to have a delta G of formation of 0. Okay, so then basically you just take the products minus the reactants here, so negative 269.6, and they show this here, but negative 269.6 kilojoules per mole. And you have to multiply that by 4, because there are 4 moles in this equation. And then you subtract that from essentially just the P4. 24.4 kilojoules per mole times 1 mole, if you want to be really careful about how you're showing this here. Okay, so then once you subtract those two from one another, if the chlorine was something other than chlorine, we would have to multiply by the 6 as well. But since it's 0, obviously 6 times 0 is 0. So that's going to give us 1102.8 is the kilojoules for that one. So the delta G for this reaction, is this reaction spontaneous? It's a negative delta G, so this is very spontaneous, right? It's because it's a fairly large number for the delta G. It's just, you kind of have to shift your brain a little bit here when you're thinking about these, because a positive delta G means it's not spontaneous, and negative delta G means that it is. The other question here, what is delta G for the reverse of the above reaction? So what would the delta G be if we flip it? Any ideas? Yeah, it does the same thing that delta H does, basically. These are all state functions, so they all kind of react the same way. So you flip this, you end up with 1102.8 instead of negative 1102.8. So the reverse reaction, what can we say about that? It's not spontaneous, right? So reactions, probably sensing a trend here, they're only spontaneous in one direction. Not the band. Sorry, I don't know why I said that. I think that's pretty much it for today. Yeah, because then we're talking about free energy and temperatures. That's going to be a nice short one. This stuff is really not all that bad. The next couple of sections will be a little bit harder, but honestly, the only thing you really need to know from that one is how to use your delta G's of formation, just like your delta H's of formation, and then how to use that equation where you're using the delta H and the delta S to calculate the delta G. All right, we'll see you in class.